Hi, this is Arash and welcome to the Epoxy channel. In this channel, we're gonna talk about the epoxy resins from the theoretical specs to the most practical ones. So if this is the first video you're watching, or if you're interested in epoxy resins, please like and subscribe to our channel for more videos. Today, I'm going to present Thixotropic Fillers Amending Flow Properties. Controlling flow is a part of the epoxy formulation process, which is important for several reasons. For example, for mixing and metering consistency of the epoxy formulation, for ease of application, for example, for brush, spray, trowel, penetration, etc., or to induce specific features, for example, providing sag resistance or thixotropic properties. The bottom line is that these rheological properties must fit the desired method of application. These factors are generally controlled by manipulating rheological properties through the application of the fillers and diluents. The use of solvents and diluents has been presented in a separate video, and here the role of fillers and additives in controlling the rheological properties of epoxy systems will be discussed. Control of viscosity in coating and adhesive applications can be challenging. For example, the resin product may need different flow characteristics at different times. For wearing out the surface, they must flow readily. Yet, they should also exhibit sag and slump resistance and no adhesive run or bleed. Rheological additives often used to amend flow properties in epoxy systems. Rheological additives may also provide other benefits in the system, including lower required energy for pumping, mixing, spraying, prevention of phase suppression, promoting suspension, increasing cohesive strain, improving the surface texture, and reducing formulation cost. The role of solvents and diluent was to reduce the viscosity of the epoxy resins. However, there are certain occasions when the need is to increase the viscosity. For example, in the case of adhesives, the viscosity can be increased by the addition of fillers. Fibrous fillers cause a large viscosity increase than do particulate fillers. Finer filler particle sizes having a large surface area will greatly but not always result in higher viscosity than equal concentration of larger particle sizes. Increased viscosity might be desirable for adhesives. However, too high viscosity can yield undesirable processing properties. Therefore, maximum filler loading is often set by the optimum viscosity. Figure shows the obtained viscosity versus weight percent of various fillers in diglycidyl ether bisphenol A epoxy diluted with dibutyl phthalate. The other role of fillers is to control the thixotropy for avoid sagging. Some applications require that the product be flowed for mixing and applications, but it must not flow or sag once applied. This property is called thixotropy, which means that material undergo a decrease in viscosity when they are subjected to shearing, for example, using a brush to apply paint. Thixotropy provides a shear thinning effect. That is, viscosity decreases as the shear rate increases, and vice versa. This effect has been depicted in this image. Certain fillers can provide thixotropy. The thixotropic fillers work by forming a temporary structure in the mixture, generally the result of van der Waals forces, which can be broken down at high rates of shears. Thixotropy can be obtained at fairly low loading concentration with colloidal silica or fumed silica, precipitated calcium carbonate, certain clays, cellulose, and other fibers, bentonite, metallic leafing powders, and hydrated magnesium aluminum silicates. A good thixotropic filler usually has the ability to interact with the polymer matrix via dipolar and/or dispersion interactions and the ability to achieve polymeric entanglement. Fibers with the branch-like fibrils with high surface area and surface activity can promote rheological effects. Cellulose fibers, for example, interfibre RT cellulose fiber form, are perhaps the best examples of these thixotropes. The cellulose fibers' low specific gravity, 1.1, relative to other filler materials also contributes to weight saving and further improve the sag resistance of these systems. Today, colloidal silica or fumed silica, which is an amorphous silicon dioxide, is the most common thixotropic agent in epoxy resins. Fumed silica is generally incorporated at concentration of less than 10 pph, often in lower viscosity resins. Unlike precipitated silica, fumed silica has no internal surface area and possesses a high surface area to weight ratio. Therefore, only a minor amount of fumed silica, 1 to 5% by weight, could be enough to achieve thixotropic properties. The surface chemistry of the fumed silica is extremely important, and generally 3 types of chemical groups can be found on the surface depending on the processing procedures: isolated hydroxyl, hydrogen-bound hydroxyl, and siloxane. The isolated and the hydrogen-bound hydroxyl groups are hydrophilic sites, whereas the siloxane is the hydrophobic site. Thus, fumed silica grades are generally characterized by their surface area and whether they are hydrophilic, standard grade, or hydrophobic. The hydrophilic silica is most effective in nonpolar and medium polar media. The performance of hydrophilic fumed silica is often improved by adding a polar substance such as ethylene glycol, glycerin, or some secondary amine to the formulation. In medium polar to polar media, hydrophobic fumed silica is more effective thickening agent and generally preferred. Hydrophobic fumed silica is also noted for providing superior moisture resistance in adhesives, sealants, and coatings. The thixotropic characteristics provided by fumed silica are due to its ability to develop a loosely woven, lattice-like network by hydrogen bonding between particles. This network raises the apparent viscosity of the system, increases the cohesive forces, and contributes to the suspension of the solid. Because the hydrogen bonds themselves are relatively weak, they are easily disrupted through the action of an applied stress or shearing force and quickly reform when the stress or shearing force is removed. Parameters that are important to the performance of fumed silica system include the nature of the resin system or the polarity, concentration of silica, grade of silica used, particle size, surface area, density, surface chemistry, etc., degree of dispersion, and finally presence of other additives in the formulation. To ensure proper dispersion, the addition of silica to the formulation in the right sequence and the effectiveness of the dispersion equipment are very important. High shear mixing equipment will improve the efficiency of fumed silica in the formulation. Often, silica should be added to the resin directly or to more viscous part of the formulation with a little solvent or diluent as possible. Dispersing the silica in a concentrated base or master batching provide optimum efficiency and stability. Incorporating the silica before adding any fillers or pigments ensures homogeneous distribution. Finally, the fumed silica is often used in 100% solid liquid resins and result in a surface that is free of texture. The fumed silica also prevents other components from settling, while the extrusibility and spreadability is unaffected. In most liquid epoxy resin systems, fumed silica is only employed at 1 to 3 weight%. Precipitated calcium carbonate and other minerals are also used for thixotropic properties. Precipitated calcium carbonate (CaCO3) is also a low-cost extender, often used in the 14 to 50 weight% ranges. Ultrafine, below 100 nanometer precipitated calcium carbonate with surface areas from 15 to 13 square meter per gram provides the greatest efficiency. CaCO3 is hydrophilic and has a tendency to agglomerate in organic polymers and plasticizers. In hydrophobic systems, precipitated calcium carbonates are generally surface treated to render them hydrophobicity to improve their dispensability. Conventional surface treatment of CaCO3 is with fatty acid, whereas types of fatty acid yield subtle differences in filler wettability and polymer compatibility. Other mineral additives, which are considered to be very cost-effective rheological additives, including kaolin, hydrated aluminum silicate, bentonite, hectorite clay, talc, also called magnesium silicate, and atapulgite, hydrated magnesium aluminum silicate. Kaolin and talc are considered to be viscosity thickeners, whereas atapulgite is more of a conventional thixotrope. Kaolin is a common filler used primarily as an extender in adhesives and sealant formulations. Depending on the grade, kaolin can also control viscosity to prevent drip or sag, improve surface smoothness, provide reinforcement, and also reduce shrinkage. The finer particle sizes, for example, particle size of 0.5 micrometer or less, build viscosity more efficiently and provide better reinforcement than do their coarser counterparts. The finer particles of kaolin occur as platelets, and the coarser particles form stacks or books of platelets. Kaolin is relatively soft and it is non-abrasive. Here again, the key parameters is choosing a particular grade, for example, of particle size, shape, and particle distribution, etc. Kaolin is also available in hydrous and calcinated grades. Special surface modifications are available to further improve reinforcement. The objective of the surface treatment is to increase filler loading and or improve physical properties without loss of rheological characteristics. A variety of surface-modified kaolins have been introduced, including clay treated with silane, titanate, polyester, and metal hydroxide. Sealant-treated kaolin is used in applications requiring maximum sag characteristic in the service environment. Bentonite is a white, gritty, abrasive colloidal clay that is both hydrophilic and organophilic, which is used in emulsions, adhesives, and sealants. A microscopic particle of bentonite is composed of many thousands of stacked and or overlapped submicroscopic flakes. Talc is a hydrophobic and organophilic filler, often used as an extender in epoxy adhesives and sealants, but it also has flow control properties. Talc is used in higher solids, high viscosity applications such as caulking compounds, automotive putties, mastics, and sealants. Thin platted particles have aspect ratio varying from 20:1 to 5:1. Coarse particle sizes 10 to 75 micrometers are commonly used at loading levels of 5 to 13%, whereas fine talcs 1 to 10 micrometers are more expensive and require intensive dispersion processes. Platigarates also enhance barrier properties and air, water, and chemical resistance. Compared to polymers filled with standard particulate talcs, polymers filled with plated talc exhibit higher stiffness, tensile strain, and creep resistance. These properties are maintained at both ambient and elevated temperature. Surface treatment for talc particles include magnesium and zinc stearates, silanes, and titanates. Atapulgite is a very cost-effective thixotrope, but unlike kaolin or talc, it is not used at high loadings and thus is not considered as an extender. Atapulgite consists of needle-like particles with a size of about 0.1 micrometer. Thickening occurs upon the mutual separation of individual particles as the porous mineral surface is exposed to surrounding medium and forms stable colloids. Cationic surfactants often enhance the performance of autoapulgite thixotropes in organic systems. Typical usage levels range from 2 to 8 weight%. Autoapulgite particles are easy to disperse, and at 10 to 20 weight% loadings, it can be considered as a partial asbestos replacement in polymeric-based sealants for the construction and automotive industries. Molecular fillers such as glass and plastic are also used to provide non-sag properties in epoxy systems, with a different mode of operation though. In fact, microcellular fillers drastically reduce the specific gravity of the product. As the adhesive or sealant is lighter, there is less stress on the adhesives or sealant due to the forces of gravity. Microcellular fillers, such as glass microballoons, are commonly used in synthetic foams. However, they are expensive raw materials. Cibrico Corporation of Hawkins has recently introduced a new relatively inexpensive filler called Seal Cell, which is a micron-sized multi-wall hollow glass filler in size range of 1 to 115 micrometer. The particles have both spherical and irregular geometries, which is claimed to provide advantages in improving tensile strength as well. Thanks for your attention. I hope you find this video interesting. Please share your thoughts, comments, or questions, and I will come back to you soon.